So our first speaker is Dr. Daniel Huppmann. He is the scientific lead of the modeling platform development team in the energy program at the International Institute for Applied Systems Analysis in Luxembourg. So he studied mathematics at the Technical University of Vienna and subsequently obtained his PhD in economics at the Technical University of Berlin. Among other positions, he then held a postdoctoral fellowship at Johns Hopkins University, where he also worked for the civil engineering department and was a visiting fellow at the think tank Resources for the Future. He has then also worked for the German Institute of Economics Research, and he is the lead developer of the open source modeling framework Message IX. And he was also an author of the 2018 IPCC Special Report on Global Warming of 1.5 degrees. In his talk, he will tell us about synergies and trade-offs between climate action and sustainable development, as well as open tools to explore scenario ensembles. So the attendees will be free to ask questions on the Q&A tool at any time, and then we will be asking these questions at the end of the talk, as Anya anticipated. So Dr. Huppmann, the stage is yours.
Okay, thank you very much. I really want to thank the organizers for inviting me and for putting this really important topic of climate change on the agenda for this year's symposium. As Anya already said in the introduction, the climate crisis is an urgent topic, and I just want to reiterate something that Ursula von der Leyen said a few days ago. There will be a vaccine against coronavirus, and coronavirus is obviously affecting our lives at the moment quite a lot, but there will not be a vaccine against climate change. So keeping this topic on our radar and trying to find solutions for that is really important. And with that, I want to jump into my presentation. If you go back 1.5 years ago, you had a lot of headlines in newspapers, and the media, like this one from the New York Times about a major climate report describes a strong risk of crisis as early as 2040. And this report that is mentioned here is, of course, the special report on global warming of 1.5 degrees C, SR15 by the IPCC, where I had the honor and the privilege to contribute to. And I want to focus on one sentence from this New York Times article, namely, the greenhouse pollution must be reduced by 45% from 2010 levels by 2030. And in particular, this statement, you saw that in a lot of media outlets, journal articles, etc. And what I want to end up in my talk on is, how did we actually get to this number? Where does this number come from? But before I tell you how we got to that number, I want to give a brief introduction of climate change and the Sustainable Development Goals, then talk about how we did qualitative assessment of mitigation options in the special report, and then move over to the quantitative model-based assessment that we did. And in particular, I want to talk about the measures that we took in the report to focus on transparency, reproducibility, and fairness of our assessment. And then towards the end, I want to show how this scenario ensemble that we developed can be used to gain some insights on the Sustainable Development Goals. And then I want to end on some near-term policy outlook. So what is climate change? Why not go to the special report on 1.5 degrees C, in particular to the glossary in the annex. There are a lot of definitions. And then if you read the definition of climate change, it refers to a change in the state of the climate. And so far, not so surprising. But then if you read on, there are 3 issues I want to highlight. First, we are talking about climate change as something that has to be identified. So we want to do science about this. It has to be measurable. The second part is that it's not just about the mean, but it's also about the variability. It's the special report on 1.5 degrees C of warming, so the global average of the temperature increase. But what is really important to keep in mind that this average hides a lot of the variability, increased risk for droughts, increased risk for flooding, increased risk of wildfires. And this is all hidden when you only look at the average. So the variability is really important here. And the third aspect is taking how the United Nations Framework Convention on Climate Change actually defines climate change, and that is that we're talking about climate change as what is attributed to human activity, either directly or indirectly. So how has the climate changed over the last 50 years? This is a figure from the Summary for Policymakers from the IPCC Special Report. And over the last 50 years, the global mean temperature has increased by roughly 0.7 degrees. And if we continue with the current trajectory, we're going to exceed the 1.5 degrees C threshold by roughly 2040. So in the next 20 years, give or take. What we have done in this, or what this figure shows in the IPCC SR15 is if you decrease your emissions very drastically, then you have a reasonable chance of staying below 1.5 degrees C. But the important part is you have to decrease your emissions very drastically. And the figure on the bottom right of this slide shows that you have to reach net zero by either 2055 or 2040 to stay in these ranges of exceeding the 1.5 degrees C. So these are very drastic changes. That is it's a very substantial transformation that needs to happen in our society. Now you might think, why is 1.5 degrees C so bad? I mean, it doesn't sound like a lot. So I want to show you some work that my colleague Edward Byers has done recently, and which was then taken up in a very good article in Nature. So what Edward Byers and colleagues did was look at different risks arising out of climate change. For example, heat wave exposure, water stress, risk to power production. And then they looked at, well, in a 1.5 degrees C world, how many people are exposed to these risks? And in particular, heat wave exposure, you have 4 billion people exposed to these risks just at 1.5 degrees C, which doesn't sound like a lot. What they then also did was see where are people that are actually affected by several of these risks. And then they drew these very nice maps where you see, well, in particular in the Indian subcontinent, you have a lot of people affected by several of these risks very strongly. And that is only at 1.5 degrees C. If you then say, well, what happens at 2 degrees C? You have 6 billion people exposed to heat waves. And you see that now a lot larger part of the population and a lot more regions are exposed to multiple of these risks at the same time. And then if you think, okay, 2 degrees C is even still very ambitious to reach, what happens in a 3-degree world? And then you see you have almost 8 billion people. So basically the entire world population exposed to heat wave, half of the population of the world exposed to water stress. And you see that if you look at the map on the top right of this slide, you basically have on every continent people exposed to multiple of these risks. So this is why climate change is really important. And our human perception of saying, well, it's only 1.5 degrees, it's only 2 degrees, because this only focuses on the average and doesn't take into account the variability, it misses a large part of the important picture. Luckily, 5 years ago, there were 2 big policy agreements to tackle this problem. And if I ask you which one comes to your mind about a landmark agreement in 2015, then everybody will jump up and say, well, obviously the Paris Agreement. And I will say, not quite, not what I meant, because before the Paris Agreement, there was actually another agreement reached, the 2030 Agenda for Sustainable Development, in September in New York, not Paris. And what happened at this meeting was that the UN agreed on 17 goals, going from zero hunger, no poverty, good health, education, to clean and affordable energy, to circular economy, to good life on land and good ecosystem in the oceans, and also one of these is the climate action sustainable development goal. Each of these goals is linked to a number of targets, and each target is linked to a number of indicators, so that it's not just we want to make the world a better place, but the policymakers very specifically said we want to make the world a better place, and this is how we are going to do it by setting these targets, and this is how we're going to measure whether we have actually reached these targets by setting very specific measurable indicators. So that was the one agreement. The other landmark agreement was the Paris Agreement, adopted by the Conference of the Parties, COP21 in December in Paris. And it aims to keep warming to well below 2 degrees C and pursue efforts to limit the temperature increase to 1.5 degrees C. And if you paid attention on my previous slide, then you know that there is actually a very big difference in the impacts to mankind, whether we end up in a 2 degrees C world or a 1.5 degrees C world. Now, if you read the fine print of the IPCC special report, you will see that the long title actually has sustainable development in it. So while the headline statement is obviously global warming 1.5 degrees C, and these are the issues that a lot of the media focused on when they reported on the findings of the IPCC, then there is actually quite a lot of content related to sustainable development. And now I want to switch to how we went about in this report to do a qualitative analysis of climate change mitigation options and sustainable development. What we set out to do in chapter 5 was to provide a review of synergies and trade-offs between different mitigation strategies to combat climate change and the 17 dimensions of the Sustainable Development Goals. So we reviewed dozens of scientific manuscripts and meta-studies, and we tried to map that to the 17 SDGs, 23 mitigation options, which can be grouped as energy demand, energy supply, and then measures related to land and oceans. And these include efficiency improvement, switching from fossil fuels to renewables. Nuclear is an option that is on the table. Carbon capture and storage, so burning coal or biomass, but then not releasing the CO2 into the atmosphere, but capturing it and putting it into geologic storage. So these are the different options that we analyzed here. For each of these indicators, we wanted to know what is the direction. Is there a positive correlation between the mitigation option and the SDG, or a negative one? So positive is a synergy. For example, by restructuring the power sector, the energy supply sector, to be more climate friendly, we can actually go a long way towards meeting SDG 7 about clean and affordable energy for everybody. But then there are other mitigation options and sustainable development goals that actually contradict each other. And there you have then trade-offs, whether you try to reach the climate goal, but have negative impacts on the SDGs, or you try to tackle the other SDGs, for example, making clean water available to everybody, but which might stand in the way of the most effective options to mitigate climate change. And then a fourth dimension that we analyzed here is the level of confidence. Is there only one study that looked at some particular combination of these? Or are there many studies? And do these many studies agree? Or do they show sometimes yes, sometimes no? We don't know, maybe. So there are 4 dimensions how we try to put that picture of the synergies and trade-offs together, and that then you end up with a very big space that you need to map. And we had a lot of discussions on how to actually communicate our findings here. And what we then came up with was this figure 5.2, which is extremely dense because there is a lot of information hidden or embedded in it. If I can talk you through this briefly, the first wheels on the left, so this one and this one, are about the energy demand options. The second set of wheels here and here are the energy supply options. And the third one are the mitigation options related to land and oceans. On the top, you have the synergies. So you have the positive correlation or positive interaction between mitigation options and the SDGs. On the bottom, you have negative interactions. The stronger the color, the more agreement and confidence we have in these findings. And the longer the bars that are here, the longer the bars, the stronger is the effect, either negative or positive. And then the circles indicate all the SDGs. So it starts over here from SDG 1, SDG 2, etc. So this is how we tried to condense all the information that we collected in a huge table on the interactions into something that you can visually digest to some extent. And I invite you to then go to the report and look at this table in more detail. I just want to highlight one finding in particular, and that is that if you look at the energy supply options, there are a couple of red parts. So where there are trade-offs between using energy supply options to mitigate climate change. There are a lot of green synergies as well. But if you look at the energy demand options, like increased efficiency, like fuel switching, then there are even more synergies between mitigating climate change and the SDGs. And there are a lot less trade-offs. So the high-level message that this picture is trying to convey is it is much easier to meet the SDGs and mitigating climate change if you focus on the demand side. Now, this is what I wanted to show you about the qualitative assessment. This will not give you a statement like I showed you from this New York Times article about reducing by 40% by 2030. For that, you need a quantitative analysis of pathways. So this will now be the second part of my, or the third part of my presentation. This ensemble of pathways reminding you of this New York Times article. Where did we get this number of reduction by 45% by 2030 from? What you may want to do first is you open the report and you read the summary for policymakers. And here you will find the long version of the statement in the that was mentioned in the New York Times articles. In model pathways with no or limited overshoot, then CO2 emissions declined by about 45% from 2010 levels by 2030, and there is an interquartile range, because of course this is the more scientific approach, not the summary that the newspaper reports on. So here there are definitions, there are model pathways, they are defined as no or limited overshoot, and we also not just report the average of all the pathways of 45%, but we also show what is the range. I want to talk more about what are these models that delivered these model pathways. And the tool that was mostly used in this context are integrated assessment models. And they aim to encompass the entire human and Earth system. So if you think about it, you're a PhD student, you want to know something about, for example, the energy system. This is a very good starting point. Then you start building a model of the electricity sector. And then you say, well, coal and natural gas are important inputs into the electricity sector. So you extend your model to look at extraction and mining and fossil resources. And then you say, well, fossil resources is probably not good if we want to do something about mitigating climate change. So I should add renewables here and make a good description of wind, solar, but also biomass, because biomass then can also be used as biofuel and directly feed into your demand sector. And then you realize we are not really interested in gasoline or electricity per se. we're interested in the services that energy provides to us. So mobility, lighting, heating, cooling, etc. And then you have a reasonable description of your energy system. And then you realize, well, renewables, in particular biomass, where does that come from? So I need a representation of forests, I need some representation of land use. And then once you start investigating that, you realize, well, land use, there is competition for food, because we can't just use all the crops for biofuels. We also need to make sure that people have enough to eat. So then you start including agriculture and food demand into your model. And then you say, well, I still don't have my climate represented here. There are emissions from fossil resources, there are emissions from land use and agriculture. So then I need to add a climate system representation to my model. And the climate system, you can't do that really without oceans, so you need to think about that as well. Then you start wondering, well, agriculture and also extraction and mining, you need a lot of water. And water is of course also really important. SDG 6, sanitation, so you need to include that in your model. And then you worry about health, which is also an SDG. So you start wondering about air quality and you try to include that in your model. And then from there, go to the social dimensions of health and poverty. And once you have that, then you have a reasonable starting point for doing integrated assessment of the energy system, land use, climate, and other aspects that are relevant when you study the SDGs. You can differentiate this figure into 3 aspects. On the top, you have the aspects related to the biosphere. In the middle, you have the economy. And then at the bottom, you have the human needs. And of course, this is my very integrated assessment modeling centric perspective. In the next talk by Rupert, he will talk more about forestry. So then you could, from this part of this chart, go open up a whole new field of study, looking at forests and land use in particular. And then later on, Lisa Bock will give a presentation about climate system modeling, whereas in our integrated assessment world, we only usually have a very stylized representation of the climate system. And then she will talk about how you have these huge Earth system models that you need supercomputers to run. And she will talk more about the interface to other communities and other, well, from my point of view versus another community. And she will talk about what this community does. So this is the type of model that was used for this analysis. And now I want to say, how did we actually go about collecting this information? What the IPCC does is it assesses the available scientific, technical, and socioeconomic literature to understand what is climate change, what can we do about it, how can we adapt, and how can we mitigate it. And in most cases, it is sufficient to just read the manuscripts and do a summary of these manuscripts. And for this qualitative analysis that I showed you a few minutes ago, that is perfectly fine, you can do that. But if you want to look at the model outputs to really make an assessment, well, how much do we have to reduce CO2 emissions to stay in a 1.5 degree pathway? Then just looking at the published materials in the manuscripts is not sufficient, because usually the numerical model results are not presented in the same data format. Usually these studies do not show the entire data from the model output, but only what is relevant for this particular manuscript. And then also definitions and units differ. So you cannot, for this quantitative assessment of pathways, just go read the manuscripts and download the supplementary material and do a meaningful assessment of that. So what has been happening for the SR15 and already for previous reports by the IPCC is that there was a systematic community effort where the IPCC and the Integrated Assessment Modeling Consortium, so the umbrella group of research teams doing integrated assessment modeling, came together and did a community process of compiling quantitative pathways into a common database. And this database was hosted at IIASA. And this is also how I got to be part of this roller coaster that was the SR15. The aim here was to provide the authors with a curated set of scenarios and pathways that they could then analyze in the chapters. And what we also wanted to do when setting up the process for the SR15 was really make a step towards more transparency and more reproducibility of the assessment. So what we did was develop a suite of tools to make it easy to dive into not just a report, but into the data that powers the report. What is an important concept in the IPCC process is the line of sight. So if you read the summary for policymakers, you will see there is more to read about that in chapter 2, section 4. Then you go to chapter 2, section 4. There you will have a summary, which will again send you to further down into chapter 2. And then at the end of this process, you will see, well, these are the studies that supported the argument that we made in the summary for policymakers. So you go from the summary all the way down the rabbit hole to the scientific literature that supports this finding or this assessment. And we wanted to do something similar on the data side. This is, for example, figure 2.4, which shows some trajectories of population, GDP, and food demand in these quantitative pathways that we compiled. This is as it is printed in the report. And then you can say, okay, this is a nice figure, intuitive, okay, but I want to know more. So we developed an interactive online scenario explorer where you can visualize this data, and then you can have a mouse over and you can say, well, there is this one line. Why is this one line higher than all the others? And then you can click on it and it will direct you to the manuscript where this particular scenario was published. So you can read more, why is this scenario different from the others? That is a point and click kind of tool. So something that even people who are not very sophisticated with scientific programming will be reasonably comfortable to use. But then you can say, okay, I don't want to point and click. I want to look at the code. So we also made the source code that was used to generate a lot of the figures in the report open source. So you can go to this website and here you can look at the source code that was used to generate this figure 2.4 and many other figures. So you can read the code and you can say, okay, this is how they went about it. This is how, which steps they had to do for cleaning up the data, for categorizing. And then you can say, okay, I don't want to look at code. I want to run the code. So then you can go to GitHub and you can download this repository and start working with this. For example, you can say, there is a particular set of scenarios that I think are weird or that they have issues. So I want to exclude them from my analysis. So then you can easily, in this code, add one or two lines that says, well, exclude the scenarios from this particular study because I think this study shouldn't be used here. And then you can recreate the figure, excluding a set of scenarios or adding scenarios that you developed with your own model just recently and say, well, how do my scenarios actually fit into the larger picture of the SR15? I'm already talking longer than I expected to. So I wanted to talk a bit more about increasing fairness of the IPCC assessment, where FAIR stands for findable, accessible, interoperable, and reusable. And what I wanted to talk you through is for each of these different aspects, which all are aimed towards increasing the openness of science, I wanted to talk you through how we actually went about doing that, but I will skip ahead because I'm running out of time. I just want to show one.
You still have 5 minutes just to give some ballpark. Okay.
Yeah, but I have more slides at the end. But yeah, just one thing that I thought was really cool a few weeks ago, my colleague Nico Bauer wanted to share some of the data that they have done with the Remind model and which was used in the IPCC SR15. And what you would have done previously was probably you make a figure, you make a snapshot of the figure, you put the snapshot of the figure in an email and you send that email to other people. But what this scenario explorer that we developed for dissemination of the SR15 allows you is to create workspaces and then share links to these workspaces directly. So then he made this predefined workspace, and if you click on this link, then you will directly end up in our scenario explorer and you will see the data that he referred to. And you can then use all the interactive tools that we developed here directly out of a tweet, for example. And I think that this is a really nice illustration of how you can make science more open by using social media, for example, to have then direct links to the more technical, more sciencey tools that we developed around this exercise. One other thing that I wanted to show you is how to deal with data errors. Right? Nobody likes to do errors, but already when writing the SR15, we were aware that if you have these huge numerical models, there will be errors. Either because the modeling teams realized that something was wrong in their model, or because during the assessment, I, as the chapter scientist for the SR15 or one of the authors, misinterpreted something. So right from the get-go, we wanted to keep something, have a tool that allows us to see what is wrong in the report. And for that, we used GitHub issues. So you can go to this GitHub repository, which also has the assessment notebooks used to generate the figures and tables, what I just mentioned earlier. And here everybody can say, oh, I think there is an error in this particular figure, or there is something weird in this model. And in this way, we can also do the tracking of errors in an open and accessible way. And a lot of the questions were answered, but then a few things were actually really incorrect, where models had given us incorrect data. So then we made a new release of the data. And if you go to this interactive scenario explorer, there you will actually have a detailed list of all the changes that were made at various points since we published the report, with links to the GitHub issues where it was discussed whether this was really an error. So again, we try to be transparent, not just about the process of how we derived figures and tables, but then also what happened after the publication of the report, and allowing everybody to see how we deal with these issues, possible errors. Now, I want to talk briefly, how do you actually use this scenario ensemble? Now I talked a lot about how we collected it and what we did. Well, I didn't talk as much as I was planning to, but about what we were doing to make this open and fair. And now I want to show you how you can actually use this scenario for analysis of the SDGs. And this is from figure 2.4 that I already showed, two important indicators across these pathways, population and GDP, related to SDG 8, in particular the gross domestic product, so that a good economy is part of the SDGs. And what you see here is that there are pathways that reach the 1.5 degrees C temperature goal. So these are all the pathways that are marked in blue. There are pathways that are compatible with the Paris Agreement that have high or low population growth, or that have high or low GDP. So this is to show, well, it doesn't mean that to reach the Paris goals, we have to tank the economy. No, there are pathways out there, numerical model quantifications that show you can have both growing GDP, but still be in line with the Paris Agreement. A similar aspect is on food demand and final energy demand. Again, the blue pathways are those that are compatible with the Paris Agreement and the 1.5 degrees C temperature ambition. And what you see here is that there are pathways that have a lot of energy demand, which is then used for, generated mostly from renewables and nuclear, or low energy demand. So you don't need to stop consuming energy to meet the Paris temperature goal. Let me show you something briefly about carbon capture and sequestration. As I already said, burning fossil fuels or biomass, and then storing the CO2 and putting it into geological formations to sequester it. And there is a lot of discussion whether CCS is really necessary to meet the Paris temperature goal. And on the top, you have all the 1.5 degree scenarios. At the bottom, you have all the 2 degree scenarios. And what this shows is that there are some scenarios here that do not need any CCS to meet the 1.5 degrees C temperature goal. There are a lot of scenarios that use it, but what this quantitative pathway ensemble shows you is that there are some pathways that could actually reach the Paris goal without relying on CCS. There is one more slide that I'll jump over to get.
Okay, thank you, because we are very tight on time, so this will be a good time to wrap up if you can.
Yes.
Thanks.
My apologies. I wanted to briefly mention the United in Science synthesis report that came out last fall as a follow-up to the SR15 and other initiatives. And just to say, the current policies are insufficient to meet the 2 degrees C target. That is not a surprise, and not even the lockdown as a result of coronavirus will really help us to get in a better direction towards Paris. So what we need is a ratcheting up process. So we need to become more ambitious, and in particular, the short-term measures that are no regret options, that don't hurt, and that can easily, in particular now with a coronavirus recovery program, actually be very helpful, both for the recovery, but also in the long term for climate change. These measures are increasing efficiency, electrification of the demand sector wherever possible, decarbonizing the power sector, so stop coal and also reduce gas, and then replace residual fuels, in particular in the transport sector. I want to use 20 more seconds because this is the Young Scientist the Young Scientist Symposium, and I wanted to make a reference to the Young Scientist Summer Program at IIASA. So at our institute, every summer, about 50 PhD students from around the world come and work with us for 3 months. And if you're interested, if you are a PhD student and work on some topic that is related to the SDGs or some other aspect where IIASA might be a useful collaborator, then please check out this website. And for this year, it's already closed, but for next year, for summer 2021, it would be great to have many applications from whoever listens to this symposium today. With that, thank you very much.
Okay, thank you very much, Daniel, for the very, very interesting talk. We have some questions for you from our participants. So the first question is, where do you see the strongest leverage for implementing mitigation measures? So in other words, how to implement the knowledge to achieve real impacts based on the results of your analysis?
Yeah, thank you. In addition to these 4 measures that I mentioned here, one thing to keep in mind, coming back to an earlier point, is that you should not look at mitigation options in isolation. You should always consider how does it impact the other SDGs, and are there some synergies that can be raised. And in particular with these 4, increasing efficiency, electrification, decarbonization, and replacing residual fuels, there are a lot of synergies to be raised. In principle, what we found in chapter 5 is that looking at the demand sector and options there is a better strategy than looking at the supply sector. So rather than building new renewable power plants, let's see if we can change our demand and behavior to consume less electricity for starters. One point that I want to mention, or one reference, is the project drawdown. There are a lot of solutions that can be implemented right away. And project drawdown is one initiative that has a lot of options off the table where they say, look, this could be started right away. So that is something where you might want to start looking for good ideas.
Okay, thank you very much. We have a few more questions. So another question is, can you measure how robust the results are with respect to incorrect data of a single study, for example?
Yes, well, so one complicated point is that this should not be seen as a statistical sample, this scenario pathways. We have about 400 scenarios in there that were found from various studies from multiple modeling teams. It is not a statistical sample, so you should not interpret it as such. It is always good to think and verify whether the findings that you have make sense. So if you think, well, there is one outlier, then even if the scenario is not incorrect per se, maybe it is not a good answer or a good application of the research question that you are trying to answer. So it's maybe not so much a question of is the model or the scenario correct or incorrect, it's more a question of is this scenario that I'm trying to use actually useful for the question I'm trying to answer. But this is less a question of statistical robustness and more of a read the paper, try to understand what the authors try to do. Does that make sense?
Yes, that's very clear. Thank you very much. So I think we have time for one more question at least. So this is, there is another question. So you briefly mentioned that there are pathways to achieving the 1.5 goal without carbon capture and sequestration. So our attendee asks how they look like. So what is special about them? Is there some feature that distinguishes them from the other ones?
Yeah, there is one study in particular that we developed at IIASA, led by Arnulf Grubler, and it was published in Nature Energy. The low energy demand pathway. And there we spent a lot of time thinking about how demand behavior could be changed. So there, this scenario, the scenario development was started with the intention, we want to have a scenario that does not require CCS. And then, okay, how far can we get in other sectors, in changes in mobility behavior, changes in electricity generation, changes in food demand, going to a less meat diet or no meat diet, and then seeing how far we could push each of these individual societal choices to get to 1.5 degrees C. And it is a very strong push. I think that this scenario is a really interesting case of you can do it, but it will require a very drastic reconfiguration of our everyday lives, in the sense of only eating meat on very special occasions or not at all, not needing a car, not needing cars anymore, and not just not having cars, but actually building cities in a way that you don't need cars, but that you can do much more by public transport. And this is what I indicated earlier. I think the coronavirus recovery could give us a lot of entry points into implementing these measures. And it is now up to the policymakers to actually take this opportunity and lead the way.
So perfect, we are perfectly on time. Thank you very much again for the very, very interesting presentation and your replies. They were very enlightening and opened up this world of integrated modeling, scenario ensembles. So thank you very much again.